Dear students, good morning to all. So today we are going to see about the topic of singly reinforced rectangular beams. So already we have discussed about the design procedure for the singly reinforced beams. First we want to know about what is meant by singly reinforced beam. So already I told that if the reinforcement bars has to be provided in the tension zone, then the beam is said to be a singly reinforced beam. So in the compression side, the concrete has to withstand the strain. So there is no need to provide in the compression zone. So we need to provide the bars in the tension zone. Then the beam is said to be a singly reinforced beam. So today we are going to see about the design of singly reinforced rectangular beams by using the limit state method. Okay, so already I have told the design procedure for this. So today we are going to see about a problem. The problem following that the design a singly reinforced concrete beam to the following data. Okay, so this is the question. They have given the data as clear span as 3 meter. So with the supports is 200 mm. So live load is given as 6 kilonewton per meter. So the concrete grade is M20 and steel grade is Fe415. So these are the given data which is given here. So we need to calculate the AST, that is how many bars we need to provide, that we need to go to find it out for this problem. Okay, so for this we are having multiple steps. I already told in the design procedure. So the first step one is to calculate the basic data which is need to calculate for the problem. Okay, so the step one is we need to find it out the stresses. That is the for this they have given as M20 grade concrete. So the FCK, characteristic compressive strength, is denoted as FCK. So it is 20 Newton per mm square. So the grade of steel is given here as 415 Newton per mm square. So Fy we have to take it as 415 Newton per mm square. So next the live load is given here. So we need to take it in account. Okay, so this is the first step. So next we need to go for the cross section or dimension of the beam. So here they didn't give any dimension here. So we need to assume the dimension or cross section of the beam. So we need to assume the width and the depth of the beam. We need to assume the width and the depth. So how can we calculate the width and depth of the beam? As per IS 456 code, the span to effective depth ratio for simply supported beams or slabs is given as 20. So it is available in the page number 37 in the code book. So span to effective depth ratio for the simply supported beam is 20. So span we have to take it as capital L and effective depth as small d. Okay, so we have to denote the overall depth, the capital D, overall depth as capital D and small d as effective depth. So the span is given here as 3 meter. So we have to convert it into mm. So 3000 mm. So 3000 mm divided by d is equal to 20. So we need to find out the value for small d. So small d is is expressed as effective depth. So effective depth d is equal to 150 mm. By solving this, we can get the value of effective depth as 150 mm. So next we need to assume the effective cover. So effective cover, already we know that the effective cover, it is the distance between the center to center distance between the bar to the surface of the concrete. So this is said to be the effective cover of the member. Okay, so effective cover we need to assume it as 40 to 50 mm for the beam. So assume d dash is equal to 50 mm here. So we need to calculate the overall depth. So overall depth in the sense we need to capital D. Yeah, it can be calculated by adding the effective cover as well as the effective depth. Okay, so effective depth here found to be 150 mm plus effective cover we have to take it as 50 mm. So by adding these two values we can get the overall depth as 200 mm. Okay, so overall depth as 200 mm here. So we need to take take B as 200 mm. So we need to take the we have to assume it as a square beam. Okay, so take it as B is equal to width of the beam as 200 mm. It is the assumed value. Okay, so we are going to check the trial and error method. So whether it is suitable or not. At the step 5 we need to check for effective depth. At that time we have to check the dimension of the beam. So whether it is adequate or not. So we have to do the trial and error method. So assume it as 200 mm. Okay, so the dimension of the beam should be taken as 200 mm by 200 mm. The next step is to calculate the effective span of the value. So next step is to take the effective span of the value. So we need to the following condition has to be considered. We have to take the least value of the following condition. Okay, we have to take the least value of the following condition. So the condition is first condition is we need to find out the center to center distance between the supports. Center to center distance between the supports. So the beam is placed on the supports. Okay, the beam is placed on the supports. We have two supports. On the two supports, the beam is horizontal member is placed. So the overall span, the length of the beam is given as 3 meter. So the width of the support is given as 200 mm. So this, we need to calculate the center to center distance. Okay, we need to calculate the center to center distance between the supports. So 200 mm is given in the question. So we need to center to center distance means we can calculate a point 200 mm divided by 2 plus 200 mm divided by 2. So two supports are there. So 200 divided by 2 in the sense which is 100 mm. So it can be converted into meter. So they are given as here 0.10. Okay, so given as 0.10. So 3 plus one of the support is 0.1 meter and the another support is 0.1 meter. So the center to center distance between the supports is 3.2 meter. So the next condition is clear span plus effective depth. So clear span is given here as 3 meter. So effective depth we assumed it as 0.15 meter. Okay, 0.15 meter. So it can be calculated by adding this. We will get the value of 3.15 meter. So we are having two values here. So one is 3.2 meter and 3.15 meter. So we have to take the least value. So the effective span can be taken as 3.15 meter here. So the effective span, the value of effective span can be taken as 3.15 meter here. So next we need to calculate the self load calculation. So next we are going to calculate the load calculation. So in that load calculation, we have to consider the loads given in the question. In addition to that, we have to assume the self weight of the member. So self weight of the member in the sense it is the dimension into the unit weight of the concrete. Okay, so self weight is to be considered as unit weight of the concrete multiplied by the cross sectional dimension of the beam. So cross sectional dimension of the beam here is B into capital D. So width into overall depth into 25 is the unit weight of the concrete. So self weight can be calculated by using this formula. So 0.2 we have assumed as 200 mm by 200 mm. So 0.2 into 0.2 into 25 will get the value of 1 kilonewton per meter. So self weight is 1 kilonewton per meter. Next one is the live load is given there. So live load is taken as 6 plus self weight is 1. Then finished load, we have to assume the floor finish or finished load. So it can be taken as 0.75 to 1.25. Okay, so 1.25 kilonewton per meter. So it can be taken as the 0.125 meter. So okay, so 6 plus 1 plus 0.25 will get the adding. We have to add the self weight of the beam, the live load, then the finished load, everything we have to add, consolidate. So after that the total value was found to be 7.125 kilonewton per meter. Okay, so it is the total load acting on the beam. Okay, so since we need to provide so the total load was found to be 7.125 kilonewton per meter. So since it is a limit state method, we have to multiply the load factor value here. So we have to multiply the load factor value here. So the load factor value was found to be 1.5. So we have to convert the normal load into the factor load. Okay, so we have to multiply the total value load by the factor value. Okay, so factor value is found to be 1.5. So the factor load value was found to be 10.68 kilonewton per meter. The total load value was found to be 10.69 kilonewton per meter. So next we need to calculate the value of bending moment and shear force. Okay, so since the beam is simply supported carrying UDL, the bending moment formula can be calculated by using this formula. So mu is equal to W into L square divided by 8. So W, the value should be taken as the factor load value. So factor load value was found to be 10.68. and the effective span value. So we need to we have to take the effective span value. You should not take the clear span value. Okay, so effective span we have calculated in the step 2. So we have to take the value of effective span here. So 10.68 into 3.1 square divided by 8. So after that we can get the value of mu. So it is equal to 13.24 kilonewton meter. Okay, so 13.24 kilonewton meter. So next we need to calculate the value of shear force. So shear force value was found to be maximum shear force is equal to WL by 2. So since it is simply supporter carrying the UDL, so the shear force value is found to be WL divided by 2. So W, the value is the ultimate factor load value. So factor load value was found to be 10.68. So the effective span value was found to be 3.15. Okay, so effective span value was found to be 3.15. So by using these values we can calculate the value of shear force here. Okay, so shear force value was found to be 16.82 kilonewton. Okay, shear force value was found to be 16.82 kilonewton. So these are the basic steps. So we need to calculate the value of AST in the next step. So next step is the step 7. So in this value we need to calculate the value of AST. Okay, we need to calculate the value of AST. So the value of AST can be calculated by using the formula. It is available in the code book. Mu is equal to 0.87 Fy AST into D into 1 minus Fy AST divided by FCKBD. So this formula is available in your code book IS 456. So substitute the value of moment here. So moment value was found to be 13.43 into 10 to the power 6. So it is equal to 0.87 into the Fy value is the here we are taking the Fe 415 bar. So the Fy value was found to be 415 into AST we need to calculate here. So into the effective depth it should be 160 into 1 minus AST into 415 divided by 200 into 160 into 20. Okay, so this is the thing. So by using this after calculating this we will get the value of AST as 285.21 mm square. So AST as 285 mm square. So next we calculate the value of minimum AST. So minimum AST was found to be the formula 0.85 into B into D divided by Fy. Okay, so after substituting the values here we will get the AST minimum as 65.54 mm square. So hence the design is safe. We are proceeding the correct way. So next we need to find out the diameter of the bar. So assume diameter of the bar. So after that we can get how many bars we need to calculate. Okay, so assume the diameter of the bar as 12 mm here. So by using this the number of bars was found to be, it can be calculated by using the formula AST divided by area of 1 bar. Okay, so AST divided by area of 1 bar. So by substituting the value of AST here 285.21 divided by area of 1 bar was found to be, it is circular in section, so pi by 4 into 12 square. So after that we are getting the value as 2.52 here. Okay, so 2.52 approximately we can take 3 numbers of bars here. Okay, so we need to provide the 3 numbers of bars in the tension zone. Okay, so area of 3 numbers of bars can be calculated by using the formula 3 into pi by 4 into 12 square. So we'll get the value of 340 mm square. So we have to provide 3 numbers of 12 mm dia bars as in the tension zone and 2 number of hangers bars in the compression zone. Okay, 2 numbers of hanger bars in the compression zone we need to provide. So next we need to calculate the shear. So shear we need, for that shear check we need to consider the 2 values, that is tau v and tau c. So the tau v value can be calculated by using the formula VU divided by BD. So it is the formula which is available in your code book, page number 72. So by substituting the value here we will get the value of tau v as 0.53 Newton per mm square. Okay, so 0.53 Newton per mm square. So next we need to calculate the value of tau c. So it is a permissible shear strength. So for that we need to calculate the percentage of tensile reinforcement. From the table number 19 we need to calculate this value, tau c value. So in the table number 19 value, they have given we need to find out the percentage of tensile reinforcement. Okay, so percentage of tensile reinforcement can be calculated by using the formula 100 AST divided by BD. So 100 into 340 divided by 200 into 60, 160, we'll get the value of percentage of tensile reinforcement as 1.06 percentage. Okay. So from this we need to calculate the value of tau c. So by using the direct value